Here are a couple more examples of static problems. In order to help you guys out, I have a step-by-step method that you can follow. So the first step is always going to be draw a picture. And not just any picture, draw a picture that shows only the x and y components, or the parallel and perpendicular components of force. The next step will be to write out Newton's second law for your x and your y. Two separate equations. Okay. The third step will be, so this step is a lot of words. It seems complicated. If you have two equations and two unknowns, you'll solve one equation for one variable. So you'll have x in terms of y, and then you'll plug that back in to your other equation. It's weird to put it in words. It's a lot easier just to see me do it. So, the final step is to solve everything, which is easier said than done. So, let's get started with an example. There's a 5 kilogram block hanging from three strings, right? So we shall call them tension 1, tension 2, and tension 3. So if you notice, I picked a point where the three of them converged, and I made that my point of interest, and I drew all the forces originating from that point. So our first step is going to be getting the parallel and perpendicular components, or the x's and y's. So, for T1, I have it drawn there in yellow. So, if that angle is 70, that interior angle is also 70, because it's parallel lines cut by a transversal. So, in my x, I have T1 sine of 70. In my y, I have T1 cosine of 70. Okay, so we're going to do the same thing for T2. So my 60-degree angle is right there in the top right. So my x component is going to be T2 cosine of 60, and my y is T2 sine of 60. Now we have a T3. And we're not sure what to do about that yet, so let's redraw our diagram first. And that pesky T3. So right now, I could write my x equation and I could write my y equation, but I have this T3 that I don't know anything about. So three unknowns and two equations isn't going to work. So let's draw a free body diagram just for the block. We can do that because the acceleration of everything in the system is 0, including that point and including this 5 kilogram mass. So the free body diagram for the mass has tension T3 pulling up and the block's weight pulling down at 50 newtons. So we can do Newton's second law with this. So the sum of the forces is equal to 0 because it's a static problem. So I get that T3 is equal to the weight of the block. And I mean, if you look at it, it kind of makes sense that one little string has to support the entire weight of the block. Good. So now that I know T3, I have two equations and two unknowns. So let's start with my y equation. Sum of the forces is equal to mass times acceleration. We know the acceleration is 0 because it's a static problem. Positive T2 sine 60 minus T1 cosine 70 minus T3, which was 50 newtons, is equal to 0 newtons. So I'm going to make it a little prettier. It's equal to 50 newtons. Okay. So that's all I can do in a y, because right now I've written one equation and it has two unknowns in it. So I'm going to turn to my x, I'm going to write it over here. Sum of my forces is equal to ma Again, that acceleration is going to be 0 because it's a static problem. So t2 cosine 60 to the right minus t1 sine 70 to the left is equal to 0. I'm going to rearrange it, and I'm going to solve for t2. This is part of step 3. I'm going to get t2 in terms of t1. So I have a statement that says t2 equals t1 sine 70 over cosine 60. So now that I have t2 in terms of t1, I can plug it in to my earlier equation. So instead of writing t2, I'm going to write t1 times sine 70 over cosine 60. So all that was t2 times sine 60 minus t1 cosine 70 equals 50 newtons. I can factor out that t1 divided by cosine 60 minus cosine 70. All that is equal to 50 newtons. So I'm going to plug that mess in parentheses into my calculator and do 50 divided by that mess. When I do that, I get T1 is equal to 38.9 newtons. So I found T1. Now that I found T1, I can plug it in to my second equation. And I get T1 is 38.9 times sine 70 over cosine 60. And I get 73.1 newtons. So that one wasn't too bad. Let's do another one. So this is two blocks that are connected by lots of strings and a pulley. So the top right angle is 60 degrees, and that angle in the middle is 100 degrees. And I'm going to be looking for the tension in all of the strings as well as the unknown mass over on the left. So the first thing that we got to do is draw some forces maybe. So once again, I'm going to pick that junction. So I have T1, T2, and T3. I don't like that 100 degrees in the middle. That's not a right triangle, and that's unpleasant. So I do know that the top right one is 60 degrees, so I know that the angles of my triangle have to add up to 180, so that angle right there, sorry it's so small, has to be 30 degrees. And then on the other side, to add up to 100, my yellow angle has to be 70 degrees. Okay, so this is looking a little better. I'm going to break up the forces over here so you can see it a little better. So for T1, my 70 degree angle is in my lower right. So my x is going to be T1 sine, because that'll give me that top opposite side. And my y is going to be T1 cosine 70. For T2, I'm going to use my 30 degree angle. My x1 is going to be, once again, sine. My y is T2 cosine 30. Okay. So let's go ahead and take care of our T3. We have that 5 kilogram mass with T3 supporting it and its weight pulling down. So it's just like the one before. I'll do the sum of the forces is equal to mass times acceleration. So T3 minus 50 newtons is equal to 0. And I get that T3 is just equal to 50 newtons. While we're at it, let's go ahead and look at the free body diagram for the unknown mass. Since it's on a pulley, that tension is the same throughout, for now at least. The tension is going to be the same throughout. So I just get that T1 is equal to its weight by the same process we did with the one right above it. Okay, so we have two equations and two unknowns because we solved for T3 already. So we can write our Newton's second law for our x and our y after we draw the picture. T1 cosine 70 going up, T2 cosine 30 going up, the weight pulling down, and then left and right, T1 sine 70, and T2 sine 30. Okay, now our x's and our y's. For our y, we know that the sum of the forces is equal to 0. So T1 cosine 70 going up plus T2 cosine 30 also going up minus the 50 newtons going down is equal to 0. So just make this a little prettier. T1 cosine 70 plus T2 cosine 30 is equal to 50 newtons. That's all I can do with the y. Now let's look at the x. So once again, the sum of the forces is equal to ma is equal to 0. So T2 sine 30 to the right minus T1 sine 70 to the left is equal to 0. T2 sine 30 is equal to T1 sine 70. So once again, we want to get T2 in terms of T1. We want to get T2 by itself, so we can plug it into our first equation. So T2 is equal to T1 sine of 70 divided by sine of 30. So now we're going to plug it into our y equation. So we still have T1 cosine 70, plus we're going to plug in T1 sine 70 over sine 30 for our T2. All that times cosine 30 is equal to 50 newtons. I'm going to factor out T1. I get cosine 70 plus sine 70 cosine 30 over sine 30. All that equal to 50 newtons. So now I plug that mess into my calculator, and then I do 50 newtons divided by that mess. I get T1 is equal to 25.4 newtons. With that T1, I can plug that into my second equation, my x equation. So I get T2 is equal to 25.4 times sine 70 over sine 30. When I plug that in, I get T2 is equal to 47.7 newtons. Okay, so we know all three tensions now. Our T3 was 50, our T1 was 25.4, our T2 was 47.7. We still haven't found the mass of that little block on the left. So to do that, we go back to that free body diagram that you've probably forgotten by now, the one all the way over on the left with that unknown mass. So we take that and we're going to write an equation for it. So T1 is equal to mg. We know T1 now, so it's not that big of a deal. So our mass is equal to T1 divided by 10. So 25.4 divided by 10 gives me 2.54 kilograms.